Hello, this is John Mount from WinVector LLC, and I'd like to go through this talk that I'm titling Preference Inference Using Stan. And this is going to be something we show how to do from R. So who am I? I'm John Mount, a general partner at the data science training and consulting company WinVector LLC. I'm known as the co-author of Practical Data Science with R, now in its second edition. And I'm also the co-author of the vTreat R package, which is a specialist package for re-encoding high cardinality explanatory variables for predictive modeling. WinVector LLC is a statistics, machine learning, and data science consultancy, and we're looking for introductions. And you can also follow us on the WinVector blog. Now, to talk proper, what I'm going to do is I'm going to bring up a problem, which I call learning to rank, and some history of that. Then I'll bring in Stan and use Stan to solve the problem. And we'll work through this together, and we'll then come to some shared conclusions or recommendations. So what is the problem? The problem is learning to rank, which is super popular in online and offline retail. The problem is we show a user or a prospect a number of alternatives, in this case, 5 glasses of wine. And at best, we know which wine they selected. Whereas internally, we know the user probably has a preference or even a rank preference for each of these wines. So which wine they pick, if any, is very much affected not only by the qualities of the wine at hand, which they do not tell us, and also the wines it's competing with, both in positive and negative ways. So our goal is to estimate the hidden or unobserved intrinsic preferences that our users, our group of users that are thought to instantiate one persona or cluster of users, have. Which wines do they like and how much? This allows us in our business goals to simulate that user in our back-end systems when doing retrieval, finding wines to show them, doing sorting, our presentation order. This goal of measuring intrinsic preference eliminates some rank systems such as XGB Ranker because its API is given a panel of wines presented, it will then repredict which ones picked without showing its internal structures. So we want to basically specify an imaginary system where the user forms internal preferences of wines and then externally observably picks the wine. So for a formal setup, we're going to have to show more examples than any one user would tolerate. So as is common in marketing, we're going to group the users into personas, sets of users thought to be somewhat exchangeable or equivalent. As I've said several times, we unfortunately do not observe user preferences, we observe only user behaviors. Typically, we show them a panel of 5 items, say web items to buy, wines, parking spots. They maybe pick none, reject the whole panel, or maybe they pick one, which is very informative about the one they picked, but tells us very little about the ones they rejected. This family of problems is typically called learning to rank, and it's a very classical statistical censoring problem that we don't have the data we're trying to learn, we have only the behaviors. The history that I know it as, being a computer scientist, largely goes through Thorsten Jochum's and his optimizing search engine queries through click-through data. And there's a lot of nice surveys on this. And basically, the field in the computer science field, seemed to abandon statistical methods in the in the 90s due to poor performance, and then treated this as a quadratic optimization problem. Though even the criticism seemed to say that statistical methods probably were up to the task, they just weren't performed well enough. So this is the problem, and maybe it could be an easy problem. If, for instance, all the panels or lists we showed to people had only 2 alternatives, then this is exactly the interview sequence you'd do in a conjoint analysis. And it's roughly solvable by logistic regression, or logistic regression on pairwise differences. So there's ways to deal with this. However, maybe things are quite difficult. There can be a lot of confounding factors that we may want to model. We're not going to model them here, but going forward, this will become very important to us. So user behavior may be based on pick position. For instance, in web search, it's well known that people don't scan past the first 2 entries. Or it could be the irrelevant alternative are recentering effects, that showing a very expensive item in a list makes people more willing to pay for somewhat expensive items. And you just can't say this enough times. The data is incredibly censored. When they tell us only 1 out of 5 positions is selected, that's only about 2.3 bits of information. So each panel we're presenting, we're extracting very little information. And finally, the thing that keeps me up at night is the people that reject the entire panel. They pick no wines whatsoever. It could be an interested party that didn't like any of the wines we showed, or it could be a window shopper, somebody with absolutely no intent to buy. And therefore, the fact that they rejected all the wines is not, in fact, informative. One is left with a lot of alternatives, like maybe only keep the panels where one was selected, or maybe have enough demographic data on the user to accurately identify motivated or qualified leads. Let's go back to our wine example and make this concrete. The data is going to be generated in an artificial example and read these columns left to right in time. So each panel or group of wines has a number. So the first 5 rows of this system are group 0, the next 5 rows are group 1, and the last 5 rows are group 2. In each group presentation, each wine has a presentation position. 0 is first in the list, 4 is last in the list. We can model the position as being part of the selection process or not at our choice. Each wine presented has an ID, and that's given in the example index. So the first wine in the first panel is wine number 7. We use this as a lookup key to find any properties of the wine, which themselves can be explanatory variables. Acidity, alcohol level, level of tannins, whether it's a red or white wine, variables like that. The next 3 columns are our pretend variables for our wines, and they're simply just named X1, X2, X3. And we're just showing them taking very simple values. And these X variable values would be completely visible to our model. Our model would see these explanatory variables. The next few columns, score and hidden activation, are not observable to our model, but this is how we're imagining the user's choice process works. What the user does, or at least what the idealized modeled user does, is they evaluate a logistic style function, giving a probability score, what their probability of accepting the wine is. And this is landed in the score column. Then they flip coins proportional to these scores to build up the hidden activation column. So in the first row, they said this is a wine that I sort of have a 29% chance of liking, and they turned out not to like it. Whereas in the 5th row-enabled 5, they said they had a 54.6% chance of liking the wine, and they flipped the coin and actually decided to act on it. Finally, we get to our observable column, selected. A wine is modeled as being selected if and only if it has a hidden activation and it is the highest score among all the hidden activations. So in the first group, there were no activations, so there are no selections. In the second group, there was actually 4 activations, some due to very high scores, some due just to perverse chance. And the one with the highest score was then selected. And so this is modeling a very simplified user that is saying, is the wine above my standard? And of the wines above my standard, take the maximal one. This lets us model quite a lot of noise in the selection process. And again, the last column is our observable outcomes, our dependent variable to be predicted, and the X columns and the position are our explanatory variables to try to predict that. And what we're missing is, again, the score column, which would make this a regression, or the hidden activation column, which would make this just a logistic regression. We're unfortunately seeing only this heavily censored and contaminated selection column. We can re-illustrate this generative process in time again. Just to say it twice, we have some chance of retaining that. There is the presentation of the 5 wines or 5 selections candidates to the user. This is an experimental design consideration. There's possibly good things about experimental design, like we might be picking wines at random to build a very powerful experiment. And there's bad things about experimental design. It could be that the best wine is always in position 1, making that sort of confounding nuisance variable position even harder to solve for. So it could be that some business needs are actually working against us in this process. But, that's the nature of statistics. If the problem were easy, it wouldn't be ours. The next stage is, as explained before, we imagine the user has some sort of internal score or affinity for each wine, which we model as a logistic regression. We're not claiming they actually perform one of these in their head, but we're modeling their preference on some sort of abstract scale as a logistic regression. Then the user is excited about wines or not with a chance equal to this modeled probability. So in this case, the user scored 3 wines and they happen to activate 2. These are the green check marks in the third row. And so the purchasing process is they've tasted all the wines, they've formed their internal opinions, they've activated on 2 of the wines, and then they go for the highest scoring wine they activated on. Adding this activation, deactivation step lets us model quite a lot of noise in the selection process, which I think would be quite difficult without. We also can model more noise in the link space of the logistic regression. We're going to use Stan as our big hammer to solve this problem. So we've been working very hard to shape this into a Stan-compatible nail. A natural question at this point is, what is Stan? Stan is a Markov chain Monte Carlo sampler. It is possibly superior to any such sampler you're going to implement on your own because it actually uses Lagrangian dynamics in a very clever way, which I think is very effective. Stan can be used for complicated Bayesian inference. Basically, we, for Stan, write down how likely a joint state of our data and our unknown parameters is for specific values of the unknown parameters, like saying things like the user's unlikely to select wines they don't like. Stan, given this joint assignment of everything, including unobserved hidden values, returns how much it likes that value and then also samples from that distribution, allowing us to sample plausible simultaneous settings of these variables. It's a fairly high dependency system. It requires a C++ compiler and linker, and for simpler problems, it may be competitive to use Torch to capture the function and use that instead. However, I tend to prefer Stan. Let's move on to our solution. Given everything we've said, the mathematical abstraction of our abstract model of a user is as follows. We want Stan to find for us the logistic regression this one user cohort or persona is using. And we're going to model that as it's a linear functional beta plus beta 0 being the intercept that we then run through a sigmoid or inverse logit. So the Stan is to propose different values of these unobserved model parameters. Then the user is modeled as having a noise in that modeling space. So we're actually saying the user's score is not exactly beta 0 plus xi dot beta. It's beta 0 plus xi dot beta plus a noise term. The additional j is which wine in the panel. So indexing is not too important here. So we're going to model the user as forming a noisy link score on the scale minus infinity to plus infinity, and then we'll run that through the sigmoid to get it into a probabilistic scale of 0 to 1. This is standard logistic regression. We're also going to evilly approximate this noisy link score with its expected value a few places just to make, in an unjustified manner, the calculations much, much easier. And that's really my first lesson in working with Stan, is at too high a level of purity, you just don't make progress. At some point, you have to approximate things instead of making it a pure exact model. So given this setup for a list with no selection, so a panel of wines where the user selected nothing, that's our datum. For this panel of wines, the user selected nothing. How likely is that outcome given the hidden parameters? Well, the probability of observing that data, given the hidden parameters and state, is to not select any wine, they have to reject them all, which we're going to model as the and of they rejected each and every wine. If sigmoid of beta 0 plus x dot beta is the link of their selection probability, then, if beta 0 plus x dot beta is the link of their selection probability. Then by the definitions of logistic regression, sigmoid of that is the probability of selection. So 1 minus that is the probability of non-selection. We're going to treat these as independent, conditioned on some other things, or as conditionally independent. So we can approximate that entire odds of not selecting anything in the panel as the product of not selecting any one of the wines. And that's what we're writing down in this product formula. Now, for a wine where there's a selection, the thing's a little bit more complicated. So if the last formula didn't hurt your head, the next one will. We're going to instantiate the link value on the wine they chose as a variable in Stan. And that's sort of the second trick in Stan, introduce intermediate variables. So we're going to call that zeta is the link score on the wine they picked. To pick a given wine, they have to activate. Again, by the definitions of logistic regression, the probability of activating is sigmoid of zeta. Then, of all the other wines that didn't activate, none of them can outscore our wine. So basically, each other wine has to either not activate, which is the 1 minus sigmoid on that wine in the product, or if it did activate, its score has to be no higher than the wine we picked it, which is this 1 minus phi normal distribution. So this formula, which it takes about a half hour to convince oneself this is the correct formula, is what the odds of seeing this wine picked because it not only activated, but none of the other wines cut in front of it. And we're conditioning on zeta to make this product independent. That otherwise there would be a weird dependence that if this wine scored below our wine, then that would affect the odds of this other wine scoring below our wine if we don't know our wine's score. So knowing our wine's link value conditions that. So basically it's easier, long story short, third rule, it's much easier to make things conditionally independent than truly independent. So by introducing this extra variable, we can make something approximately conditionally independent. All that being said, and this sort of page takes days to develop and you get used to it, Stan will sample such that the product of the prior probabilities of beta, zeta, times the probability of observed data given these parameters is large. And then by Bayes' law, this is proportional to the posterior probability of the parameters beta given the data, which is what we want. What inference on the unknown parameters beta is the data implying? As Stan code, it's this block. Now, only the fourth portion of this block is doing any work. That's the section I've labeled the criticism. The first block in Stan tradition is the data specification. And this is essentially just declaring the types and shapes of vectors, arrays, and numbers that Stan needs to run. So to run Stan, we have to tell it how many variables there were, how many alternatives per panel. Does anyone remember what that was? That was 5. How many different panels we're going to show during training, and what the selections were. So we have all this written down. The things that Stan is going to guess for you are called parameters, and that's the next block. In Stan, unlike other Markov chain Monte Carlo samplers, all parameters have to be real numbers. So you can't have a parameter that's 0 or 1. You have to have a parameter that's in that. You can have one that's in the range. You can make it bounded reals, but it's all of its state is real numbers. And this is part of what makes Stan fast. The next block is only a notational convenience. It's called transformed parameters. And it just says, golly, I would like this x.beta plus beta 0 to have a name. Call it the link. And so it's just writing down a deterministic calculation, introducing a new derived parameter, which we're calling link, which is just the linear dot product of the parameters. That makes writing down later code more concise. The money block is this modeling block. And it lets us do two things, which we'll go into in the next slide. It lets us write down distributional facts, like beta 0 is normal 0, 10, or beta is normal 0, 10. One of those is a vector, one of those is a scalar. Stan lets us handle that quite neatly. So the little twiddle notations mean distributed as. It also lets us do for loops and if statements, which are very, very dangerous in probabilistic computation. But our for loops and if statements are only over our inputs, which are fixed in Bayesian reasoning. They're not over the parameters. So this means we're doing the same calculation independent of the parameters, which is really good. It means the calculation's not changing meaning as Stan attempts to sample. So This math block, the criticism, is saying row by row, or panel by panel, how likely is the data you claim happened given the parameters Stan guessed might happen. So to get that back down into English and math, which is a little easier on us than the Stan notation, and this is something I would copy paste and use again and again, is the Stan takes a criticism called a target. I would actually recommend not thinking of Stan in terms of prior and posterior distributions or Bayes' law, but instead as a criticism of the joint presentation of the data and the parameters that you supply the data and the parameters it's trying to guess. And the idea is if that criticism is bad, it's an unlikely pair, and if that criticism is good, it's a likely pair. The criticism is not a loss. It turns out it's higher is better, so it's not actually a criticism. I guess it's a plausibility. It's in a hidden variable in Stan called target, and Stan samples examples proportional to exponential target. So the statements that are statements like beta is distributed normal 0, 10, those are equivalent to saying target is target plus the log of the normal PDF of beta given mean 0, standard deviation 10. So the target criticisms can be encoded either one of two ways, either as distributional statements or as direct updates to the target variable. Like our first line here says target plus equals log 1 minus invert logit link. This is encoding the log probability of something not being selected. Inverse logit of link is the probability of it happening. 1 minus it is the probability of not being happening. Log probability of it not happening. Target is essentially in log units, so we want to transfer to log before that. So we can either update our overall plausibility of parameters and data jointly, either as direct target updates or as distributional statements. The art of guessing how to do that is the fun of coding up in Stan, which is basically do your mathematics first, using better math notation, then get to the Stan program. Back to our Stan code. So the only thing we care about at this point is the math. The statements on the previous page are all being translated into these math lines. The for loop is going through all of our example panels. And if the row has no selection, the target is just updated as the sum of each and every selection not being selected. And I'm using the log 1 minus notation to get better floating point performance. And then if the panel does have a selection, well then the thing has to be selected. Again, products start to look like sums because target is essentially in log units. The target has to be selected, and all the other ones either have to be not activated or not cut in front of target. And that's written down as this. Now, that is Stan, and supposedly this is the Bay Area use R group, not the Stan group. So where's the R code? Well, the R code is how you call Stan and move data in and out of it. Natively, Stan is sort of a command line system. And so there's some wrappers in R, one called rstan, and there's some wrappers in Python, one called command stan py. Do not use pystan, that's not supported, so use command stan py. But in R, you basically can give Stan either data from inside your R program or data that's in JSON format on your file system. Of course, R has tools for translating between the two, like JSON Lite. And then you call Stan. And you give it, where does it get its Stan source code? So that source code I demonstrated has to be in the file rank source censored pics.stan. You give it its data. In this case, we're giving it the data inside an R environment, so it transports it to Stan all by itself. And you tell it some run parameters, which is basically how many Markov chains to run in parallel, how many CPU cores to try to attempt, and how verbose to be while you're running. And then you also tell it what data you want back. And in here I'm saying, well, I want that vector beta back. And I want beta 0, the intercept of my logistic model back. And I want this special diagnosis variable called LP underbar back, which is proportional to target. In Python, the code is very similar, but it's written down, so it's quite easy to do. So why does this do anything we care about? Well, we want to do an inference, which means return a beta that is very high likelihood given the data. Well, by Bayes' law, that's equivalent to finding a beta such that the prior probability of beta times the probability of data given beta is high. Our Stan source code computes how plausible is the data given the parameters. So even though we might not intrinsically care about how likely is the data given the parameters, if we know that, it's proportional to how likely is beta, the parameters given the data, and Stan does all the work. So we just write the much simpler code, compute how plausible the fixed data is given this varying parameter, and the whole thing works for us. Why does that infer the right parameters? We're not minimizing any sensible loss or anything. It's basically the distribution becomes tight, and so the most plausible parameters tend to be close to the right ones under fairly technical conditions. So basically, what Stan returns tends to be right if the structure of your model is right. Now, there's a lot of worrying in using Bayesian methods. Do I have the priors right? And I can just tell you right now, once you have a lot of data, the priors aren't going to be what kills you. Getting those wrong is okay, as long as they're fairly smooth and not near zero, which you can ensure. It's getting the problem specification wrong that kills you. So what do we get back from Stan? This is what it looks like in the R end. We get back a data frame. Each row of the data frame is a different sampling event from the set of Markov chains. In this case, it returns the default 4,000 samples. Each of these samples is thought to be high likelihood. The likelihood is proportional to the exponent of LP under bar, but since they're all in the sample, we can also treat them all as plausible. Otherwise, they wouldn't have been in the sample. And it says that beta 0 tends to be a number around negative 1.4. Beta sub 1 tends to be around 0.22. So we get back possible joint, each row represents a joint value of all these parameters simultaneously being mutually consistent with each other and mutually consistent with the data. So again, each row is a possible consistent estimate of the system dealing with all sorts of dependencies. And what we can do is we could pick a row with maximal LP under bar. We could average a set of rows, or we could do other things depending on the nature of our problem. I've averaged, and this is a summary of the results. I've designed this artificial problem to have basically just 4 types of panels. So those are in the rows, type 1, type 2, type 3, type 4 example. And then the data generative process, which is how the data was made. The first type panel has an 80% chance of selecting a given wine. The second one has a 55%, and the third one 24%, and the fourth one 31%. So this data generative process is the ground truth that what's the sorry, I said it not quite right. What is the activation probability of each of these wines independent of what panels it was shown in? That's the part I got a little wrong. It's not the probability when selected in a panel. It's the probability of its activation independent of panels, which is what we want. We want to know its intrinsic or essential preferenceness. We're modeling all the interactions of being in a panel together to try to pull them off. Now, the model from visible selections and difference pairs are 2 logistic regression tricks often used in literature. Notice they get the first few wines pretty right and then fall apart. So they get the 0.8. Well, actually, the pair differences messes up earlier. The model from Stan is very right. It essentially reproduces the desirability of each wine. So what are these models? So model from visible selections. This is the common trick of just take every wine in a group as a simple yes-no problem. This is forget it's a multinomial selection, treat it as a binary selection and run logistic regression and walk briskly away. The model from pair differences is a common improvement where you, instead of modeling each wine as a rejection, you model each pair of wines where one was picked and one was not as a preference. The Stan multi-MCMC is the one we're talking about here, and the Stan optimizer is a sped up version, which I do not recommend, but it's closer to what a PyTorch style implementation would do, that you're running an optimizer instead of a Markov chain sampler. So back to our outcomes. So again, we have here the reproduction of the intrinsic value of each wine, and then in the bottom panel, and then the top panel we have the recovered coefficients. The data generative process was how the data was generated, so we want to recover those coefficients, the minus 0.12, 0.2, 0.2 in the first row. The Stan system is very close and much closer than any of its friends. And it's not just a prevalence issue. I'll skip over this, but basically once we correct the prevalence errors that are in the 2 logistic models, they don't improve much and they stop being different. So that trick of differencing isn't as clever as we think in the literature. Conclusions. These are examples where the easy preference of, hey, let's just pretend everything's a logistic regression doesn't work. Stan worked in this condition. So maybe even though this is a trivial problem, Stan is capable of outperforming logistic regression in the presence of the sort of data censoring we get, where instead of saying what wines people like, they just say which did they pick out of a group. Stan is great for prototyping because you can literally specify the probabilistic structure you think is generating the data, and you can then vary it. The tools I used were Stan R and Python. All code, including the talk, is here at this GitHub location. And I also will put that on the BARUG website. And the slides are here also in a recording of the rehearsal of the talk. This is part of our training series of trying to bring Stan into your business. And we start with a very simple problem about range censorship. Then we move up to this rank problem. And then we get to a fairly difficult time series problem. And really, if you have like to talk about this, or even better, if you have some contacts and can make some introductions, please reach out to me. And in all cases, reach out to me. I'm happy to hear from people. Thank you very much for your time and attention.